Hi, I'm David Sayers. I'm a research associate at Harvard University, and I'm out here in Kansas working with NASA's DCOTS team to study big convective storms in North America.
Hi, I'm Purva Pandey. I'm a postdoc at Harvard University working on the same instrument as part of the DCOTS team.
So we have quite a few instruments on the ER2. This is called WICOS. It stands for Water Isotopologue Integrated Cavity Output Spectrometer. It measures water vapor in the atmosphere as well as its isotopologue. So water molecules that have a slightly different number of neutrons in one of their atoms. And the reason we're interested in that is it's still water, but because the extra neutrons makes it heavier, the heavier isotopes tend to go into condensed phase, meaning into the liquid phase or the ice phase. And by looking at the ratio of this light water, that's sort of the normal water we think about, and this heavier water, we can tell something about the way water condensed in the atmosphere. So down at the surface where we are, there's a pretty standard ratio. If you look at ocean water, the ratio between the light and heavy isotopes tends to be about the same. As air rises in the atmosphere and water condenses and rains out, right, rain or snow, ice, those heavier isotopes are removed. And so in general, the upper atmosphere and the stratosphere is light in these heavier isotopes. But if you have a convective storm that's bringing ice or water from the lower troposphere into the stratosphere, that ice is going to be heavy, and so we can see that signature, and we can tell where the water vapor is coming from, and the processes that determine how much water vapor gets into the stratosphere, which is part of what DCOTS is trying to understand. So this instrument, the way it works is it uses a laser, which is in this box here, to look at one of the infrared absorptions of water vapor. So many molecules, water vapor, carbon dioxide, methane, etc., absorb in the infrared region of the spectrum. That's a region past where we can see. Sometimes we call it heat or thermal infrared radiation. So we look at a very narrow range where water vapor and its isotopologues happen to absorb, and they absorb at very slightly different wavelengths, so we can tell the difference. But there's not a lot of this heavier isotope in water vapor in general, and even less in the stratosphere. So in order to measure it, we need to be very sensitive. So this part of the instrument is a gas cell. Air flows through an inlet, which you don't see here. It's sticking on the plane, but flows through this cell. And the ends of this cell have two mirrors that are about 99.99% reflective. So light that enters the cell bounces back and forth thousands of times, creating a very long path length before that light hits our detector where we measure it. So the cell is 50 centimeters long, but the path length is about 2 kilometers. Obviously, we couldn't physically fly a 2-kilometer length cell in the aircraft, so this is a way of, in a compact instrument, flying something with a very long path length. And that gives us the sensitivity we need to measure the weak absorptions of the heavier isotopes of water vapor. The rest of this is the electronics. There's a computer. There's a board that creates the current to drive the laser. There's another board that records the signal with a very fast analog to digital converter. There are many heater controllers. The stratosphere is very cold. It can be even minus 80 C compared to where we are here. So we have to be able to not only run the instrument on the ground, we have to run the instrument at low pressure and very cold temperature. So we have a lot of different parts of the instrument that either want to stay cooler or hotter, and so we have different heater controllers to do that.
The part that's not here, our inlet, is currently installed on the ER2 plane. And that has heaters as well, so that it can, when we encounter ice particles, it can heat them and sublimate them, and so we get a measurement of the total vapor and ice. And what's cool is there are other instruments that measure water vapor, and then the difference between these two gives you a measure of the ice content.
What makes this instrument a good fit with the DCOTS project?
Okay, so well, one of the things, like I said, we're interested in convection, and so we do want to know when we're flying through cirrus, thin ice clouds in either the upper troposphere or occasionally they punch into the stratosphere. And then there's very little ice, but we do want to know when we're encountering ice. Some instruments don't measure well when they're encountering ice, so they certainly want to know when we're in ice. They know that data probably isn't very good for what they're measuring. But more generally, we're trying to understand how much water vapor is actually put into the stratosphere by clouds. So being able to measure the ice when we're flying through it tells us something about that. We're also interested in dynamics, so the motion of air. And there are very different dynamics when you're actually in a cloud versus when that cloud has evaporated and you're measuring it maybe a day later.
Now, one of the things you mentioned was condensation. But, I mean, condensation, that's just what gets on my glass when I have nice cold ice water. And so what's that have to do with the atmosphere?
Sure. Well, that's exactly right. So your glass, when it's cold, takes vapor out of the atmosphere that we're breathing all the time, we're breathing out, and it turns, in that case, into a liquid, most likely, unless your glass is really cold. And so in the atmosphere, that's how clouds work, right? So water evaporates, mostly from oceans, but from lakes, and even from the soil. And then as it rises, the air cools, right? If you go up to a mountaintop, the air is generally much colder than it is at the surface. So air tends to cool as it rises. And as it cools, just like on your glass, it condenses. And depending on its temperature, it condenses into liquid. And then if you have enough of it, it finally is so heavy it falls out of the atmosphere. We call that rain. And if it's cold enough, then it condenses, of course, into ice, and that can also fall out into the atmosphere, and on the ground we usually call that snow or frozen rain. But sometimes if they're small crystals, they stay in the atmosphere for a while. We see those clouds, nice puffy clouds. They're not rain clouds, they're just floating around, but that's all generally ice. Sometimes it's liquid, mostly it's ice if it's high enough. And so we're interested in this part of the country, we get very strong storms. On the ground, that can cause all sorts of issues for us as people. Tornadoes, or just hail, or just really strong winds. But those same storms also lift up not just ice, but also pollutants, right? If you're bringing air from the troposphere, you're taking anything that's in the air, including pollutants, and bringing it really quickly up to the upper atmosphere where usually it isn't. And that can have changes in chemistry. For example, the stratosphere we're measuring is where the ozone layer is. So you can have changes in chemistry to ozone. You can have changes to the radiation budget, so what heats and cools the planet. Greenhouse effect is usually what we call that. There's, of course, can be too much of that, but normally you'd want some greenhouse effect, otherwise our planet would be basically frozen all the time. And so that would be probably that. That may have happened at some point in Earth's past. But anyway, but these same greenhouse gases that affect the troposphere affect the stratosphere as well. And water vapor is a very important greenhouse gas, and it can affect the delicate radiation balance of the Earth. So we're also studying those effects.
Were you involved in the project last year also?
We were,
Yes.
yeah.
And so you have data from last year. I know I don't expect you to analyze the data from yesterday. Yeah.
That would be nice.
Yeah, that fast. But can you tell us, what are some early things? Have you had any aha moments, or, oh yes, that does kind of confirm moments type yet with what you're doing? Or does it take a little longer before we can get through things to do that?
Well, I'll start out with the usual caveat. This is all preliminary data. We don't have final data yet, so anything I say may be wrong. But we've seen many interesting things. One thing that has actually been somewhat of a mystery in previous field campaigns as well is sometimes we see the signature of convection, high water vapor. Maybe it's days after, so the ice has evaporated. But the other chemicals that we're measuring don't really show that it's tropospheric air. And so this mission, we were really able to measure in really fresh convection, basically when it was happening, as opposed to measuring it often days later. And so we're to see those differences between what the air is doing and what the ice is doing. And so often the ice actually ends up getting higher than the tropospheric air in the cloud. So that's one thing that we've been interested in. It's very interesting to see it sort of in real time as opposed to just hypothesizing about it after the fact, but actually seeing that this happening in a convective storm. Other things, we have many other gases. I know you've been going around talking to other instruments in addition to water vapor, and so there are interesting correlations between different concentrations of ozone and tropospheric gases like carbon dioxide and methane and water vapor. And sometimes they correlate positively, meaning when one goes up, the other goes up, and sometimes we find negative correlation. One goes up, one goes down. That tells us different things about mixing. And some of that, maybe it's been seen before, but we're seeing it in much more detail in Isotopes. We're really focused on it. We're not just sort of by accident flying through something and after the fact saying, oh, that was sort of interesting what was going on. But here we're really going after these convective storms in a fine-scale way that we haven't done before in other missions.